Hello everyone, this is another video from Easy Electric Series, and today we will talk about the 4-bit asynchronous down counter. So is it clear from the name, the down counter actually start to count from 15, it's actually count down. Next should be 14, 13, 12, 11 and end up with the 0 again back to the 15. So here you see the circuit, the design circuit. So if you compare these design circuit with up counter, there is a two big difference. Number one is the initial circuit. So if you remember, our initial pins in the up counter connected, or the clear pins, whenever you active that, it's load for 0 in your counter, because that was the up counter, so it should be start from the 0. But here, because it's down counting, actually it's you connect the old preset pins and label that the initial pins. Whenever you active this, it's actually active the old preset pins on the 4 flip-flop, and it's actually load 15 or 4-1 inside the inside the counter. So this is actually the first thing is different from the up counter. The second thing, if you compare the flip-flops, so in up counter the flip-flops was falling edge, here the flip-flops are rising edge. You see it, so you use these samples, so that means these T flip-flops are rising edge. So this is actually the second difference. So if you take a look to the circuit, it's the other thing is similar with the up counter. You have 4 T flip-flop, so the input is 4 is 1, and the clock pulse connected to the first one, the X0, the output of the first one is a clock of the second one, the output of the second one is the clock of the third one, and the output of the third one is the clock of the fourth one. So let us see how circuit works and how this circuit able to produce these actually numbers that you see on the left. So we start to check column by column. We start with review the X0 column. So this first flip-flop here is responsible to produce this column. So whenever you see the rising edge, just take a look to the input. Input is all the time is 1. It actually will be toggle. So that means in the beginning you actually active the initial, so it's actually load for 1. The X0 should be 1. Then whenever it see the rising edge, take a look to the input. Input is 1. It's we just toggle. So here you are 1. So in the next rising edge is toggle, you will be 0. You have 0, it will be toggle, will be 1. So you are on 1, it will be toggle, it should be 0. And if you check all of them, you see all actually toggle that whenever see the rising edge. So that means this is right, the first one able to produce these X0 column. So check the next one, X1. X1 is from the second flip-flop, the input is 1. The X0 connected as a clock to the X1, so that means this column that you see here is the clock pulse of these X1, and the input is 1. So that means whenever your clock, which is here is X0, is in rising edge, just take a look to the input. Input is all the time is 1. See, we put actually 1. So that means in the rising edge, it just toggle the condition that you have. So let's see, you actually start, you initialize the counter, so that means you load for 1, X1 will be 1. So then here, this is a clock moving from 1 to 0. Moving 1 to 0 is actually the falling edge, so that means the flip-flop will be hold. So see, you actually hold this one. So here it's changed from 1 to 0, that means it's toggle. If you check the clock move from 0 to 1. 0 to 1 is the rising edge. So if you check all of them, so see it is all the time hold, just whenever it's toggle, which is you have X0 move from 0, 1, that means it's actually see the actually rising edge. So that means definitely X1 will be actually the same with this column that you see. So let's check X2. If you check X2, again, this input is 1. Whenever it see the rising edge is toggle, otherwise it's hold. And the X1 is the clock pulse for X2. So that means these X1, this column that you see is the clock for X2. So again, whenever you start the counting, you active the initial pins. It's actually load for 1, so that means x2 will be 1. So then again, it's actually take a look to the clock. So see, the x1 is the clock of x2. Here it's moved from the 1 1. It's not actually the rising age, so that means it's hold. So second one is 1. So here move to 1 to 0, move 1 to 0 is a falling, not rising. Again, it's hold. So moving to 0 0 is not rising age, so again it's hold. So see, when it should be toggle whenever these clock move to 0 to 1. So that means that's rising age. Take a look to the input. Input is 1 and it's toggle, which is right. So again, for the all other 4, so again, see the rising age never happened in these 4. It's hold the 0, then whenever it's moved to the 0, 1 is rising age. It's take a look to the input. It is 1, it's toggle that. So same story. So see again, it's hold 1. So here again, it's toggle. If you check the x1, which is the clock pulse, it's moved from the 0 1, which is the rising age. So that means x2 actually produce these column, and this is what we expect. So let's check the x3. x3 comes from these flip-flop, and its clock pulse is x2. So that means here, these column you see is the clock pulse for x3. So you start with, in the beginning, you active initialize pin. It's actually load for 1. So that means first x3 is 1. So then if you check this clock, which is the x2 is a clock for x3. So here to here, never rising age happen. So the only case rising age happen is here whenever it's moved from 0 to 1, which is the rising age. That's the reason you see toggle, and here to here never rising age happen, and it's hold the 0. So that means it exactly produce this column that you see. So as you could see, so this circuit, so definitely able to produce whatever you have here on the left side. So let's just simulate the circuit and make sure the circuit actually works well. So here I have the simulation. This is exactly the same circuit that I explained. But here, because I couldn't find the T flip-flop in my library, I used just JK flip-flop, connect the J to K, and I labeled that as a T. So as you know, the T flip-flop is the JK flip-flop, which is J connected to the K and labeled as a T. So that's what you see, these JK flip-flops. So the all JK or T inputs connected to each other and connect to 1, similar with our design circuit. The all clear pins connected to each other and connect to the 1, they are deactive, that's fine. So the all preset connected to each other and make the initial switch. So here you could actually just active that in the beginning of the counting for a short time, similar with what we designed. So the other thing here is important. So again, I couldn't find the falling age in my library. I couldn't find the rising age. So because in the design, if you check here, what we designed, the flip-flop is the rising age, right? But you see I use the falling age. But because I actually use the NOT here, you are able to, with using the NOT in your path, you are able to change the falling age to rising age. So see, this is actually the falling age. I use a NOT, so that means I make this actually the rising age. So similar with the others. So in our design, it should be connected to this rising age flip-flop. I use the falling age, but I connect to this. This is Q, this is Q prim. So I use the prim of this pin, which is available here. And here you have the rising, so that means I not the this is falling. I use actually the not, so that means I actually made rising age. Okay, so similar things with here. So this is actually the falling age, because I use actually not, technically I made the rising age. Same story here. This is falling age. I use the not, technically I made the rising age. So again, whenever you use the not in the path of the falling age, you could able to make rising age. Here the all of them is the falling edge, I use actually the not, so technically I made the falling edge. So that means the design is exactly the same with what we explained. So back to the circuit, just start the simulation. Just let I stop another file that I have here. So back to this design. So I start to simulate that as usual. I just active initial pins, which is load the 15. See, all of them is 4 light is on. So this is actually X. This is, let's just see what we label. So the first one is actually X0. Okay. So this is X0, 1, 2, 3. So that means this is Z, this is 2 power 0, right? So this is 2 power 0, this is 1, this is 2, this is 4, and this is 8. So I active initial pins, so it's load 15, it then should start to count to the 14. So 14, 13, 12, then you have 11, 10, 9, 8, then 7, 6, 5, 4, 3, 2, 1, 0, and back to the 15. So this is what happened, and you see what actually it's counting down. So the circuit and design is right and it works. So if you actually watch our previous video, in the one of the previous video I explained about the binary to 7 segment code converter, which was the circuit that able to convert the 4-bit binary and show that on the 7 segment, or in other words, it's able to convert binary to actually base 10 and represent that on that 7 segment. So I actually use that circuit here again. So that means if you check this and see what we have here, so just that if I could show the whole things here, it should be nice. Okay. So what you see here is the same circuit that I explained, just so I connect these 4 bits which I indicate with the LEDs to this circuit, which is the binary to 7 segment or binary to decimal code converter. So C1, 2, 3 input, which is these X0, 1, 2, 3, I connected to this circuit and it's able to convert that to the decimal or base 10. So if you are interested to know how you could design this circuit, please check the BCD, check the binary to 7 segment code converter video. So here is the same story. I just want to see that's counting on these 2 7 segment. I'm going to actually let's do back here and just stop this, back to the circuit and start the simulation. As usual, first active the initial pins, which is load these 15 that you see. Whenever you deactivate that, start to count down. Check here, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and 0, and it's again back to the 15 that as you see here. So the frequency that we use here for the clock pulse in 1 Hz, so that means it's counting every 1 second that you see here on these LCD. So I hope you enjoyed this video. Please don't forget to subscribe channel to actually support our channel and let us to produce more video. Thank you for watching this video.